We have some dielectric material in which there's an electric flux that changes with time as represented by this function, some constant times t to the fifth power. The dielectric constant of the material is given. It's equal to 2.8. The question is, what is the displacement current at t equals 1.2 seconds? Let's just use the formula for the displacement current. Displacement current is equal to the product of the permittivity of the dielectric material and the time rate of change of the electric flux. The permittivity of the dielectric material is equal to the dielectric constant K times the vacuum permittivity, which is epsilon 0. That's a physical constant. And we multiply that by the time derivative of the function that represents the electric flux. Here's what we get when we make those substitutions. Displacement current is equal to K times epsilon 0 times the time derivative of the constant 3.6 voltmeter per second to the fifth power times t to the fifth power. Let's take the derivative. So we have a constant times t to the fifth power. The time derivative of this will be equal to that same constant times 5 times t to the fourth power. This is the expression that we get for the displacement current. Let's go ahead and substitute the numerical values and calculate. We get 0.93 nanoamps for the displacement current. It's a very small value. Nano stands for 10 to the negative 9th power. The next question is, at what time does the displacement current become equal to 1/5 of this value? If you think about it, the displacement current increases with time, so the time value will be less than 1.2 seconds. Let's again set up our equation. The displacement current is a constant times t to the fourth power, and that's the only thing we need to answer the second part of the problem. So let's set up our equation for that. I sub d prime here stands for the new value of the displacement current, and I sub d is the original value, or the value that we calculated above, which is 0.93 nanoamps. And t prime is the value of time that we're looking for, whereas t is equal to 1.2 seconds. Capital C's cancel like so. And we get t prime to the fourth power is equal to 1/5 times t to the fourth power. Let's isolate t prime. Let's take the fourth root of both sides. Here's the result of our numerical calculation. T prime is equal to the fourth root of 1/5 times t. And when we plug in the value 1.2 seconds for t, we get t prime equals 0.80 seconds. As expected, t prime is smaller than t. The value of the displacement current was 1/5 of 0.93 nanoamps at some earlier time, and that time was equal to 0.80 seconds.